Hello and welcome to this presentation on detectable sequential specifications for recoverable shared objects. This is research from the University of Waterloo and it's joint work with my student Nan Lee. My name, in case you haven't met me before, is Wojciech Kolab. I'm an associate professor in the Department of Electrical and Computer Engineering. This is the outline of the talk. We'll start with a definition of the problem. We will then motivate it with some specific use cases and examples. We will discuss the solution and then briefly go over a prototype implementation and its evaluation and finish with some concluding remarks. Okay, let's start with the problem. Let's imagine that we have a distributed object or data structure. It could be implemented in a message passing model or in a shared memory model. It doesn't matter too much for this example. The point is that some process applies multiple operations, and at some unpredictable time in this execution, it fails by crashing. Now, presuming that this process has access to stable storage or some kind of non-volatile main memory, it could conceivably try to recover and resume what it was doing, but in order to do that correctly, it needs to know answers to certain questions, like what exactly happened at the time of the crash. Did the second write operation over here actually take effect or not? And in a more general setting, where maybe the operations are reads or NQs or DQs, some of those operations might return non-trivial responses. And then if we find out that an operation did take effect, we may also want to know what response it produced. Detectability is the solution to this problem, and it was introduced by Friedman, Herlihy, Marath, and Petrenk in DISC 2017. They defined it informally as follows. The data structure provides detectable execution if it is possible to tell at the end of a recovery phase whether a specific operation was executed. This is a very interesting definition, and it's natural to ask questions like, what exactly does detectability look like? Is this a new flavor of linearizability? Is it a new type of sequential specification? Or is it something else altogether? The recovery phase mentioned in the previous slide simply refers to the execution of some specialized recovery code in a single thread when a process recovers from a system-wide failure and before the threads inside that process are restarted. This exists in the context of a shared memory model with system-wide crash failures. Friedman et al. Published a follow-up paper in PPOP 2018, and there they described detectability in more detail, giving some hints as to how we might implement it. So they refer to the use of some special announcement array by which threads announce their intention to execute an operation, and which is also used by the recovery process to then indicate the outcome of any operation that was interrupted by a crash failure. Here's an overview of how this might work. In step one, some application thread writes some element of this announcement array to announce its intention to execute op, and then it executes this operation on the shared object. Then we have a system-wide crash failure followed by the centralized recovery phase where the recovery process or recovery thread updates the state in this announcement array. And finally, the application thread, when it's restarted, is able to retrieve the result of the operation by querying its own entry in the announcement array. And of course, we can rinse and repeat and reuse this announcement array over and over again for different operations. Now that we know roughly how detectability is supposed to work, we are ready to state our problem. The problem we're trying to solve in this research is to formalize detectability. Here's a quick review of related work. I already mentioned papers 1 and 2. Paper number 3 by Aitia, Ben Baruch, and Handler is, to my knowledge, the first rigorous definition of detectability. In fact, they define something called nesting safe recoverable linearizability, which solves an even more difficult problem related to nesting of detectable objects. 4 is a practical paper by Ben David, Blalock, Friedman, and Wei, where different detectable cues are compared experimentally. and 5 is a theory paper that builds on 3. Ben Baruch, Hendler, and Rusanovsky proved some space complexity bounds on detectable objects, where detectability is defined very similarly to the way it was in paper number 3. Alright, let's move on to some motivating use cases and examples. In example A, one thread performs one NQ operation, and for recovery, the only thing that concerns us is whether or not this NQ operation took effect. Example B is a little more tricky because DQ operations have non-trivial responses. In this case, on recovery, we want to know if the DQ took effect, and if so, what response did it produce. In example C, we have 2 NQ operations, and so it's not enough to know whether or not the last one took effect. We want some additional information that allows us to deduce whether they both took effect or just one of them, or maybe none of them. Here is example C with a twist. Now the 2 NQ operations NQ the same element, which makes life just a little bit more difficult. I will come back to this point later. Example D, 2 DQ operations. Once again, we want to know what happened to the last one, but we would also like to know how many elements were DQ'd by the thread. Let's pause here and make some observations. Number 1, for detectability, it's not enough just to recover the response of the last operation. Why? Because sometimes this response is trivial, like when I have 2 NQ operations back to back, they both return OK. Knowing that the last NQ returned OK doesn't tell me if I had 2 of them or just 1. Observation 2, if we could recover the arguments and the response, then sometimes this is enough, particularly when operations are always called with distinct arguments. If that assumption does not hold, well, maybe we can introduce some auxiliary arguments or use some special tags to make those arguments look different. And then recovering the arguments and responses will allow us to figure out exactly at what point in the program we crashed. Let's go back to example C for a second. We have 2 NQs of the same value A, and we can now disambiguate by attaching sequence numbers 0 and 1. These sequence numbers would be returned when we're recovering. For example, we might be told that the last operation that took effect was NQA1, but when I'm DQing elements, all I get is the A, because then those sequence numbers can be excluded. And here is example D with sequence numbers. Once again, the sequence numbers help us determine whether both DQs or only one of them or none of them took effect, in case there's not a way to deduce that from these responses, which could in fact be identical elements. Next, I'm going to describe our solution to the problem of formalizing detectability in a way that allows us to implement all the behaviors discussed up to this point. Our research is guided by the following 3 design goals. Number 1, we wish to formalize detectability by defining an abstract interface, specifically an object-oriented interface that provides special methods that can be called to query an object and find out what happened to the last operation, which may have been interrupted by failure. Number 2, we would like our definition of detectability to be model agnostic. The object-oriented interface that addresses number 1 will also address this point, and we will intentionally avoid having threads retrieve state from the object through some low-level data structures that are internal to this object, such as an announcement array. And number 3, we would like our detectable objects to be implementable on modern hardware, and in the shared memory context, we are referring specifically to current generation Intel processors with Optane persistent memory. Our formal definition of detectability is not a new type of linearizability property. Rather, it's a new type of sequential specification, which we call detectable sequential specification, or DSS. In our paper, we describe a transformation from a plain sequential specification, or SS, to the DSS, which entails the addition of certain special methods which are used by threads to declare their intention of executing an operation, to then execute the operation, and then finally to query the outcome of this operation. The DSS only specifies the correct behavior of an object under sequential access, and so we have to combine it with a linearizability-like correctness property, such as strict linearizability, to specify the correct behavior of an object under concurrent access. The transformation from the SS to the DSS works as follows. On the left here we have the different operations of the sequential specification. Let's assume the SS is for a FIFO queue and op is NQ. In the DSS on the right, we will obtain 3 methods that are specific to op and 1 generic one that will be shared by all the different ops. Prep op, or in our example prep NQ, announces the intention to apply NQ detectably in the future. Exec op fulfills this intention by executing NQ detectably. Resolve is what we call after a crash failure to figure out what happened to our NQ operation. Roughly speaking, it retrieves the result of the last operation, and we formalize last as most recently prepared. That gives a very precise meaning to the concept of the last operation. Result means the signature of the operation, including its arguments, a bit indicating whether or not it took effect, and if it did take effect, the response it produced, if any. And finally, op itself does exactly the same thing as in the original sequential specification. As you can see, we are mixing and matching detectable and non-detectable operations in the DSS, and this has 2 advantages. One is backward compatibility with the original sequential specification, and the second advantage is the ability to request either detectable or non-detectable operations at different times or in different parts of a program, depending on the needs of the application, rather than forcing all of these operations to be detectable. The transformation can be formalized in an axiomatic style, which we borrowed from the Hurley-Ewing paper on linearizability. Each axiom defines the behavior of one of the 4 operations of the DSS. The state of the DSS-based object has 3 components. There is an array A, which is the moral equivalent of the announcement array in the Friedman et al. Papers. We also have a separate response array, which I guess would be part of the announcement array. That one stores the response of the detectable operation, and there is the state S of the original sequential specification. So prep op stores the operation signature in the element of A corresponding to process PI and initializes the response to the bottom, which means the operation did not yet take effect and the response is not known. Exec op updates the state S by applying the state transition function. It also applies the response function to compute the response and stores that in an element of R, and it returns this response to PI. The resolve operation simply returns the values in the corresponding entries of A and R, and op does exactly what you think, updates S using the delta state transition function and returns the response computed using the response function rho. I mentioned earlier that sometimes we need auxiliary arguments to tell apart different occurrences of an operation that has the same signature. For example, I NQ the number 1 and then I NQ the number 1 again. Well, an easy solution is just to bake a sequence number into that value, but if we don't want to touch the value, we can add an auxiliary argument to the signature of op and store that auxiliary argument in the state component A and then return it later in a resolve. And at the same time, that argument will be ignored in the computation of the state transition function and the response function over here, so that the exec op operation produces the correct response. This collection of examples illustrates how a DSS-based read-write register would behave under sequential access in the presence of crash failures. There are 4 execution histories illustrated here: A, B, C, and D. The process follows the same calling sequence in all 4 examples: prep write 1, exec write 1, and then resolve after crashing. In A, the crash occurs after exec write 1 and resolve returns write 1 OK. The OK response indicates that the write 1 took effect. In B, the crash is a little bit earlier, and it's not clear whether the write took effect, but resolve makes this clear by returning either write 1 bottom, which means the write did not take effect, or write 1 OK, which, as in example A, means it did take effect. In part C, the crash is right after prep write, and resolve once again tells us clearly the write did not take effect. Finally, in D, the crash occurs during prep, and resolve here returns write bottom if the prep operation took effect, or bottom bottom if it did not take effect, because this is the first prep in the execution history. In case you're wondering what it's like to program using DSS-based detectable objects, I will give you a quick example now of a producer-consumer queue. First, I'll show you the original non-recoverable code, and then I'll show you the transformed recoverable code that uses a DSS-based queue. The producer in this example simply enqueues integers from 1 and upward, and then the consumer will dequeue these and print them to the screen. If there's a system-wide failure and this code crashes, we can certainly restart it all the way from the beginning, but you will print many elements in duplicate, which is undesirable. And so I would propose that for meaningful recovery, we want more precise goals, such as the producer enqueues each integer exactly once, the consumer dequeues each integer exactly once, and because there's no way to ensure that the dequeue and the print happen atomically, we may have to allow for some of these integers to be printed more than once. And so we will set as a goal that the consumer prints each integer exactly once in the absence of a failure between lines 4 and 5, and at least once otherwise. Here is the modified producer code, which now uses a DSS-based queue. The first 7 lines accomplish recovery. I assume here each thread recovers itself. I'm not considering any centralized recovery phase. So how do we do this? Well, we call resolve on our detectable FIFO queue, and that tells us something about what happened at the point of failure. It returns an operation signature and a response. If the operation signature is bottom, it means nothing was prepared. We didn't do anything before the crash. Maybe this is the initial state. So we're going to restart enqueuing at the number 1. If we have a non-trivial operation signature, but a response of bottom, it means that operation was prepared but did not take effect, and we're going to restart enqueuing at whatever number was the argument of that enqueue. And finally, if we have the signature and a non-trivial response, which would have to be OK in this case, we will restart enqueuing at a number 1 higher than the argument of that op. And then at lines 8, 9, and 10, life goes on. We're going to enqueue in a loop, except that we start from this starting point computed by the earlier recovery code. And now we call prep enqueue and exec enqueue at lines 9 and 10 as separate operations rather than having a single enqueue operation. This is the recoverable consumer code. As in the producer, we start by recovering the detectable FIFO queue, then we do some case analysis, and then we proceed with the main loop. Inside the main loop, we do exactly what you expect: prepare dequeue, exec dequeue, and then we print the dequeued element to the screen. So for recovery, special actions are required only if we crash like here, here, or here between iterations, because this is when something is dequeued and it's not clear that it has been printed to the screen. These cases are represented by a non-bottom operation signature, which will be dequeue, and then the response, which would correspond to this dequeued value. In this case, we simply print that value to the screen again, It might be redundant. That's okay, because all we care about is achieving at least one semantics with respect to printing to the screen. If I crashed here, then op is not bottom, but res is bottom, and then line 3 is omitted. Now you may notice that if I crash at this point on recovery, I'm going to redo the prep DQ operation. That's fine because it's idempotent. Finally, let's talk about our prototype implementation of a detectable DSS-based queue. This slide presents the result of a scalability experiment conducted using an Intel multiprocessor equipped with first-generation Intel Optane persistent main memory. We compared 3 queue implementations. Number 1, the Michael and Scott queue, which is neither detectable nor recoverable. That's the blue curve. The DSS-based recoverable queue, which has both detectable and non-detectable NQ-DQ operations. That corresponds to the green and red curves. And then the detectable recoverable log queue from the Friedman et al. Paper. The graph shows some interesting patterns. It captures the cost of detectability as the gap between green and red, the cost of recoverability as the gap between blue and green, and it also shows that the DSS-based queue is competitive in terms of performance with the state-of-the-art, which is the detectable log-based queue. All right, time's up. In summary, we formalized detectability using the detectable sequential specification, which has some interesting advantages because it supports both detectable and non-detectable operations. And I briefly discussed our proof of concept prototype. If you have any questions, I look forward to receiving them and hopefully answering them either during the conference or at a later time. Please feel free to email me at the following address. Thank you so much for your attention, and I really look forward to chatting with you.